And now, please welcome back to the stage, Sandy Irani.
All right, for the second talk this morning, we have a double header with John Bostanci and Sitan Chen, and we're going to start with John, and he's going to tell us about learning the closest product state.
Did I just start? Okay, hi, I'm John. I'm going to tell you about some work on learning the closest product state. This is joint work with Ainesh, Bakshi, William Kretschmer, Zeph, Landau, Jerry Lee, Alan Liu, Ryan O'Donnell, and Ewin, Tang. In quantum learning theory, we typically imagine we have the following setup. So there's some quantum experiment that creates copies of an unknown quantum state. Us, as quantum computer scientists, want to run some learning algorithm that turns this quantum state into a classical description. Okay, but typically, like an unknown quantum state will require too many variables to describe, so we imagine that we know something about this state. So here I've written it, like you might imagine that the unknown quantum state is actually a product state. And I'll just clarify that by product state, I mean unentangled across all cuts, not like a single cut, like in the previous talks, like in the talk from a few days ago. However, a lot of the algorithms that we run are very non-robust to noise. So if we made the assumption that our state was, for example, a product state, but it actually wasn't quite a product state, our algorithms might break down, and this is like a terrible thing, because either due to noise or model misspecification error, like this could happen. And to drive this point home, we can consider the following example of product state learning. So let's imagine the algorithm that we would try to do if we actually knew that our state was a product state. So here the task is to output a description of a product state given copies of it. And the algorithm we're going to do is just look at every single register, do some state tomography algorithm on them, and then stitch them together by just outputting the tensor product of the reduced states that we learn. So this will work great if we actually know that our state is a product state, but we can consider the following example. This state is 1 minus epsilon close to the all zero state, and that's definitely a product state. However, if you look at the single qubit marginals, they're just a little bit off of zero. So when you put them all together, you'll get some error that's 1 minus epsilon to the n, which is extremely, you'll get some overlap, sorry, that's 1 minus epsilon to the n, which is extremely bad. So even though there was a product state that's 1 minus epsilon close to your unknown state, you actually are going to guess a classical description that's super bad. Okay, so now you're sad. And the moral is that even a little bit, so epsilon error in your model can change the nature of quantum state learning problems. And this motivates something that we call agnostic quantum state learning. So here we're not going to make an assumption that our input comes from a particular model. Instead, we're told about some model class C, we're given copies of an arbitrary quantum state, and we have to output the closest state in the model class to the state that to the quantum state that we're given. And we usually give ourselves a little bit of wiggle room. So here's a epsilon. So instead of having to output the exact state that is the best, we can output a state that's close to the best. And okay, here I've also written that phi is in C. So this is something called proper learning. But you might also imagine you're allowed to output things that are not in C, which would be improper learning. And for those people who know about shadow tomography, you might immediately notice that if you don't care about the runtime, there's already an algorithm that does this, assuming your model class is not too large, that's sample efficient. So this is shadow tomography. You can just estimate the overlap with every state in your class and be which one's the best, and output that. But there are very few computationally efficient algorithms. So like I said, shadow tomography is not efficient. And this is kind of surprising because in the standard learning theory literature, there's been a recent explosion of amazing algorithms for things like Gibbs states, low depth circuits. Yeah, tons of things have had breakthroughs in algorithms, and we know a lot of learning theory algorithms. But in this agnostic setting, which I think is quite natural, there's almost no computationally efficient algorithms, even for things like product states, which seem like they should have nice algorithms. So the main work I'm going to tell you about is an algorithm that does agnostic learning of product states and has sample and time complexity that's roughly n to the 1 over epsilon, with polys in between. And for the rest of my time, I'm going to try to give you some of the main points of the algorithm, and in particular, I'm going to focus on two things, so we'll keep these in mind. The first is going to be making local changes to build up a global solution, so local to global. And the second point I'm going to try to hammer home is the connection to polynomial or tensor optimization. So let's go ahead. From the example we had before, we saw that we can't depend on anything about separability. So our input state will actually, even if it's only a little bit far from a separable state, it could have properties that make the local marginals useless for us. But there are two important observations we can make. So let's say we knew that our input state has fidelity 1/2 with some product state. Then the first thing we notice is that because we're dealing with product states, if we restrict to any subset of the qubits of the input state, we also have a good product state for that restriction. In particular, the best product state, if you just cut it down to the registers you're looking at, will also be a good product state approximation to the restriction of rho. And finally, there can't be too many good candidates. There can't be, so in particular, there is a pretty small net of good product states. So in this case, I've said that if you give me more than 2 orthogonal product states that have fidelity larger than 1/2 with my input, then my state would have to be trace bigger than 1, so that can't happen. So I know that there's only 2 product states that have fidelity larger than 1/2 with rho. These two together give you, or kind of motivate a subroutine, right? So if I was able to learn a list of product states that are good fidelity with the first k qubits, I know that the good product states on k plus 1 qubits are going to look like good product states on k qubits with some additional state on the k plus first register. And both those sets, so the product states on k qubits and the product states on k plus 1 qubits, are pretty small. So maybe I should be able to take the product states on k qubits and turn them into product states for k plus 1 qubits. So the main loop of the algorithm is something like this. So from k from 1 through n, so let's go through, k is going to be the size of the prefix of the state I take. If I gave you a net, pi I, so I'm taking pi to mean a product state, for the first k registers, so by net I mean that all the pi i's are good product states and they're all pretty far from each other. They're good product state approximations and they're all pretty far from each other. Find a net product state approximations for the first k plus 1 registers. Okay, so this is the local to global part. So I'm making a local update. I'm just adding an extra qubit to each of the things in the net, but I'm building up global solutions because I'm considering the first k registers of my product state and increasing the size of k. Okay. So the next step is going to be actually finding these product state extensions, and I'll just immediately, I'll just tell you that the naive thing of just taking one of the pi i's and sticking on a new state at the end is not going to work because, sticking on that extra k plus first state might degrade the quality of this product state approximation. So what I actually have to do is be willing to tweak the pi i's a little bit. So the thing that does work to extend the product state net is search in a small ball around pi I tensor phi k plus 1. So here pi I is the thing in the net for k, and then phi k plus 1 is a guess for the k plus first register. I'll look for a state in the small ball with high fidelity with rho that's also far from the other good candidates we found. Remember, the fact that the net is small comes from the fact that the things in the net are also far from each other. So great. This is the high-level algorithm for extending our net. And in the last part of my time, I'm going to try to tell you how to reduce this to some polynomial optimization. It won't get us all the way there. You're going to have to do some more tricks, but at least it'll give you some good intuition. So let's imagine that this is our candidate. So I've drawn it as a tensor product of block spheres, but 5 qubits in this case. The first thing we do is that this kind of looks messy, so how about we rotate so that all of our root candidate, this pi I tensor phi k plus 1, is all zeros. And remember I told you I'm only searching in a really small ball around the root candidate. So everything I could possibly look at in this ball is going to be supported on really low weight Hamming strings. So if I imagine looking at the first guy, Zi, the zi being the angle with 0. This guy has really small overlap with 1, and the same for the second one, and third one, and fourth one, and so on. So in order to optimize over this ball, I really only have to consider a low Hamming rate restriction of my input. So the quantum part of my algorithm is going to be to first restrict rho to its low Hamming weight, the low Hamming weight subspace, and then do tomography on that subspace. And once I've done that, I'll have learned some coefficients that I can plug into this polynomial. And this comes from just writing out the fidelity. So you can just write the definition of the fidelity and then truncate all the terms that are too large. And you roughly get this polynomial. And because of the thing I mentioned in the last slide, this is a low degree thing. So d is something that only depends on epsilon and also the maximum fidelity with the product state. So there you go. Now all I have to do is do tomography on this low degree subspace and then optimize this polynomial, and it'll spit out for me some good product state approximation on k+1 qubits, and then do this main loop, yada, yada, yada. And yeah. OK, so there's also some additional results in the paper. So in certain cases, you can do a lot better than not having to solve this. So the polynomial optimization step is quite expensive and maybe not realistic if we're actually doing this in the real world. So there are some cases where you can do better. So in the very high fidelity case, where the fidelity is greater than 1/6, there's only one candidate you have to keep around. And it turns out that solving this polynomial optimization is not as tricky as it is in the general case. If you're told about finitely many choices and all the choices are pretty far apart, then you don't even have to do any optimization at all. You can just brute force over every possible candidate. And if you allow me to do improper learning and output a polynomial bond dimension MPS, there's a way to kind of encode the entire net as a single MPS. These two threadings are also in our paper. Read the paper if you want to know more. The final thing I'll leave off on with, I think I have one more minute, is you might wonder if you can do better. In particular, the scaling epsilon is kind of nasty. But it turns out that we show that unless NP is contained in BQP, you can't have strong polynomial scaling in epsilon. And it turns out it's kind of a beautiful thing. You just run the reduction backwards. So there's a way to take a tensor and encode the entries into the coefficients of the low Hamming weight ball of some product, low Hamming weight subspace of some state, rho. And then the best product state approximation to that state is going to be exactly a good solution, a good input to the tensor. It's going to roughly optimize that tensor. And the problem of tensor optimization is known to be NP hard. OK, that's my time. And I'm going to hand off to Sitan to talk about his work on agnostic learning for stabilizer states.
Awesome. Yeah, thanks, John. I'll now be talking about some joint work with these fantastic students, Weiyuan Gong, Chia, and Zhihan Zhang, on another class of states under which you can hope to get this kind of agnostic guarantee. Right. So we'll focus for this discussion solely on stabilizer states. So just to jog everyone's memory, a stabilizer state is a state that you can prepare starting from the all-zero state and passing it through some Clifford circuit. Or if you want to think about it in terms of its symmetries, there are states for which there exists some commuting subgroup of 2 to the n many Pallies that simultaneously stabilize that state. Okay, so these states are notable in that they can be highly entangled, but by this classic result of Aronson and Gosman, they're classically simulable. And like product states, stabilizer states are one of the earliest examples of a class of states for which you can hope to learn not just sample efficiently, but computationally efficiently. Right? So this dates back to work of Aronson and Gosman in the 2000s and subsequent work by Montanaro in 2017. One way of thinking about how to learn these states is the object that you really want to get access to is this subgroup G of Pallies. We'll think of that as the stabilizer group. And if you can get access to the stabilizer group, then your job is essentially done. You can measure in the joint eigenbasis of that stabilizer group sufficiently many times, and you'll get a reconstruction of your stabilizer state. Okay, so the question is really, how do I get access to the stabilizer group? And one recipe that's emerged in these prior works is this idea of Bell difference sampling. So I won't be able to tell you specifically how Bell difference sampling works. You should think of it as some method that essentially operates with 2-copy measurements that allows you to get random access to a certain subspace that corresponds to your stabilizer group. And so if I want to learn this subspace, I'll just sample a bunch of random vectors from it. And eventually, I'll form a basis. I'll learn that subspace using Gaussian elimination, and I'm done. Okay, so why care about agnostic tomography for stabilizer states? Well, one motivation is very similar to what we saw in the product state case, which is that this algorithm I just told you about, it works great if your state is exactly a stabilizer state, but of course, in reality, we're never going to encounter such a nice situation. And the algorithm that was designed is incredibly brittle. So if I add a sufficient amount of noise to a stabilizer state, things like Gaussian elimination are just going to fall out the window. Okay? So another motivation, which I think is interesting and is maybe specific to the stabilizer setting, is that recall, these are classically simulable states, and in general, we could consider arbitrary states and ask, okay, if that state is somewhat close to being classically simulable, as measured by some notion of magic, can I still get a learning algorithm that kind of gracefully adapts to the level of simulability? And so you could consider a natural notion of magic, like stabilizer fidelity. This is just the maximum fidelity between your state of interest, rho, which might be non-stabilizer, and the closest stabilizer state, psi. Okay? And even if you don't really care about learning, you should, if you care about, for instance, quantifying the amount of magic in your given system, then agnostic tomography is a natural fit for that task. If I had an agnostic learning algorithm for stabilizer states, then I immediately get an algorithm for estimating stabilizer fidelity. I can just take whatever state that I've estimated, whatever stabilizer state I've produced with my algorithm, and measure the fidelity with respect to this unknown state. In fact, the conventional wisdom is that this notion of magic is kind of hard to estimate because you ultimately have to optimize over an exponentially large collection of stabilizer states. And so the discussion in the rest of the talk will kind of turn this conventional wisdom on its head and show that actually we can get algorithms that are quite efficient for estimating this quantity. So what's known about agnostic tomography of stabilizer states? From prior work, there's this nice paper of Weiyuan et al. That showed that in general, you can always get an exponential time algorithm. Now note that this is non-trivial because the number of stabilizer states is actually larger than x of order n. It's x of order n squared. And they're able to obtain a singly exponential time algorithm. And in this kind of high fidelity regime, which John mentioned in the context of product states, they're actually able to get a polynomial time algorithm in all parameters. When the stabilizer fidelity is above a threshold such that if your state has that level of stabilizer fidelity, there is a unique closest stabilizer state. Okay, so the natural question is there some polytime algorithm in all parameters that works even beyond this very, very high fidelity regime? And we'll resolve that in the affirmative, but before I tell you about our guarantees, let me tell you about some natural bottlenecks. Okay, so recall that the whole game is to really learn the underlying stabilizer group of the stabilizer state of interest. So let's say that I'm getting access to copies of some unknown state rho, which is non-stabilizer, and psi is the closest or a closest stabilizer state to rho, and let G be the stabilizer group of psi. Now, let's denote tau to be the stabilizer fidelity. So because psi is the closest stabilizer state to rho, the stabilizer fidelity is just given by the fidelity between psi and rho. And so here's a crucial structural result that Weiyuan et al. Showed, which essentially shows that if I run this Bell difference sampling algorithm, recall this is the one that worked in the non-agnostic setting. If I just run it a sufficiently large polynomial number of times, then I'll actually be able to produce enough generators for my stabilizer group. The issue is that I also will produce a bunch of pallies that are essentially junk. And I don't know a priori which pallies are good and which pallies actually correspond to elements of my stabilizer group. And so now these guarantees start to make a bit more sense. In general, if I'm willing to run an exponential time, there will be ways to enumerate over, for instance, all maximally commuting subsets among my pallies, and thus find the stabilizer group. And when the stabilizer fidelity is sufficiently high, I could just imagine ruling out the spurious polys by throwing out the ones which have low trace inner product with respect to my unknown state rho. So this is essentially the content of this Weiyuan et al. Result. And the challenge really becomes, if I don't make this kind of high stabilizer fidelity assumption, how do I really sift through my collection of pallies and figure out which ones are good and which ones are bad? Okay, so let me tell you now what we show. We show that there is actually a polytime algorithm in the number of qubits and in the target error 1 over epsilon, with this caveat that we need to run in time quasi-polynomial in the inverse fidelity. I'll say a bit more about this at the very end. What I like about this result is that we actually develop a broader framework for agnostic tomography that we're able to deploy not just in the stabilizer context, but for a variety of other classes of states. I won't go into the quantitative details here, but these either extend or improve upon prior non-agnostic and agnostic results. Great. So in the remaining time, I want to tell you, a bird's eye view of the algorithmic framework we develop, because it's actually remarkably simple. So it's just a 4-step recipe that we call stabilizer bootstrapping. And I'll specialize it to the context of stabilizer states. So the first step is basically what's been done before. You're going to run Bell difference sampling polynomially many times. And the hope is that if I run this enough times, I'll produce the generators I care about. But let me just throw out all the ones for which the correlation with respect to my unknown state is low. So this is exactly what was done in this high fidelity algorithm of Weiyuan et al. So if the stabilizer fidelity is large enough, this is all you need. Then you're basically done. In general, the high correlation pallies that you produce need not correspond to your stabilizer group. But if they do, OK, then I'm happy. In general, what I can guarantee, however, is that just by the uncertainty principle, because I'm only keeping the ones which have large trace inner product with rho, they're guaranteed to commute with each other. Okay? And let's say I've run this step 1 quite long, so for a sufficiently large polynomial number of samples, such that I've pretty much captured all of the high correlation pallies in my stabilizer group. And yet, if I hit this step 3, so if I haven't actually succeeded at this point, then I'm guaranteed that the high correlation parts of my stabilizer group aren't actually enough to generate the whole stabilizer group. Then we can leverage this anti-concentration result of Weiyuan et al. To get kind of like a win-win argument. This says that if I now run Bell difference sampling one more time, I actually have a non-negligible chance of hitting a low correlation pally in my stabilizer group. So why care about a low correlation pally? Well, this is where the bootstrapping comes in. I claim that if I have a low correlation pally, then I can simply measure the following 2 outcome POVM. And I'll just post-select on the outcome that would have stabilized my unknown stabilizer state psi. I get a post-measurement state rho prime. And because this correlation term in the denominator, in the normalization term, in Born's rule, is guaranteed to be bounded, right, from above, then the resulting fidelity between my new post-measurement state and the stabilizer state I cared about has now increased by a constant factor. Right? That's the bootstrapping that's going on. You've now boosted you've decreased the distance between the state that you're considering and the target stabilizer state by a constant factor. And now the key idea is I just recurse. Now instead of working with rho, I'm just going to keep working with rho prime. And the point is I only have to recurse a logarithmic number of times because I'm boosting by a constant factor every step. Okay, so that's the high-level idea. Right? So with that, let me conclude with some open questions. In the product state setting that John mentioned, one can ask, can you get a better dependence on n and epsilon for product states? Can you get a better cutoff than 5.6 for the high-fidelity algorithm? In the stabilizer context, we unfortunately incur this quasi-polynomial dependence on the stabilizer fidelity. Is this necessary, or can you actually get something that's fully polynomial in all parameters? We give some circumstantial evidence that this quasi-polynomial dependence might be necessary, at least that if I go down to inverse polynomial stabilizer fidelity, I expect some kind of super polynomial lower bound. This is all conjectural, and honestly, the upper and lower bounds, I wouldn't be willing to place a bet on either direction. You could also ask, the protocol I gave you is something that involves highly adaptive 2-copy measurements. Can you get something much more lightweight, ideally using non-adaptive single-copy measurements? There's also a question of proper learning. The algorithm that I mentioned for, briefly for learning T-dope states agnostically ultimately doesn't return a T-dope state. And similarly, you could ask the same question for matrix product states. But more broadly, I think the general question that these 2 works open up is, what are other examples of states for which we've had so many amazing breakthroughs in recent years on learning highly structured families of states? How do these results really shake up when you throw agnostic learning into the picture? And are there applications of the ideas from either of the talks that could be used to get agnostic learning guarantees in those cases? Okay. So with that, Thanks for listening, and we're happy to take questions now.
Right. So first, very naively, how come agnostic learning is the framework, the learning theory framework that's first considered, be before PAC or online learning or concept learning and so on? This is something we observed in both talks. And maybe what happens if we consider other distances beyond trace distance and fidelity, for instance, KL divergence or other classical divergences? So there's two questions there.
Well, I guess there's two parts to that question, so I'll give two answers. First of all, I think there has been a lot of work on quantum versions of PAC learning. So, it's not like we're putting the cart before the horses or something. I mean, there's been a lot of other work, and we're just introducing this. I think, it's kind of there's a cycle, I feel in science where you have problems you can't solve, you make them easier, you solve them, and you get new tools, and then you find harder problems. I think in some sense this is a natural next step. Now that we have all these tools for structured learning, we would like to relax that problem in some way. You could imagine different models of inputs or different notions of what it means to learn something, but I think that reducing or removing the restriction that the input comes from the structured class is a very natural thing to consider. I mean, obviously everyone's welcome to introduce their own model of learning and see if it leads to interesting conclusions. And then the second part about whether or not it matters if it's fidelity or trace distance, I don't know. I mean, you could take things about fidelity and use Fuchs van der Graaf to turn them into fidelity guarantees, but fidelity just seemed like a natural candidate. So it's also a good question, something to explore.
I also want to maybe add to the first part. So one thing that, so agnostic learning has been kind of studied at length in the classical literature. And I think that at least these works suggest some interesting quantum quirks to the problem that we don't see in the classical setting. So if we take something like learning parity with noise, right? So the analog of all this Bell difference sampling stuff is just pure Gaussian elimination on a system of linear equations. And we expect that once we add a bit of noise, this problem becomes hopelessly hard. But even this high fidelity result in the stabilizer setting says that, well, I can add a bit of noise, but actually it's fine. I'm able to somehow still learn this resulting stabilizer group, and things are okay. So maybe it suggests with the quantum setting, there could be settings where learning algorithms are remarkably noise robust. And anyways, that's one possibility.
Another.
I had a question over here. Thank you for the wonderful talk. So with this Bell difference sampling, you need 4 simultaneous copies in order to operate on them, and then you talked about at the end sort of doing a single copy regime at a time. Yes. I was wondering if you had any ideas on that realm, because the Bell difference sampling sort of works by sort of convolving a characteristic function with itself, and these stabilizer states have nice properties where it's you only really care about 2 local site observables, and if you could do Bell sampling on just random partitions of the qubits. Have you thought about this at all, or these directions?
Yeah. I mean, so we've been working on these things. In the single copy setting with learning stabilizer states without non-agnostically, we know how to do this with computational difference sampling and things like this. It's kind of unclear how to get this to work yet in the agnostic setting. I think we currently suspect maybe there's some parity hardness, but we're currently not able to kind of really pin down what we expect. On the other hand, there are other settings, in the context of, let's say, estimating Pauli observables, there is a big difference between single and 2 copy, even statistically, which I guess we don't necessarily see here. So it's a great question. We're not sure yet. Yeah.
Great. Thank you.
All right. I guess we've run out of time now, so we'll take a break and reconvene at 11 o'clock. Thanks. Let's thank both speakers again. Thank you.